Hello and welcome to this week's video lesson, which is going to look at soaps and detergents, part of the Nature's Chemistry unit of Higher Chemistry. So we're going to start off with learning intentions for the soaps section. So we're going to be looking at how soaps are made and the chemical reaction involved. I've said you need to give details of that, but really just focus on the reactants and products for soap making. And we should be able to describe the cleansing action of soap based on the hydrophobic and hydrophilic nature of soap molecules. So this is a really interesting little section. If you've ever wondered how soap works to get greasy stuff off, then we're going to learn that. And then finally, you should be able to draw diagrams as well to help to illustrate how soaps work. So we're going to begin with a couple of starter questions. There's 3 altogether. Here's the first 2. So pause the video now and give these questions a go. Okay, I'm hoping you've had a go at these questions. So here we go. Fats and oils can be classified as esters. They're definitely not soaps, and they are esters of glycerol and fatty acids. So you need to remember that about the structure of fats and oils. And therefore, which of these is likely to be produced by hydrolysis of a fat? Well, if a fat is an ester of glycerol and fatty acids, the hydrolysis of that ester will produce glycerol and fatty acids. Fatty acids isn't on this list, but glycerol is the correct answer to that question. Okay, starter question 3. Identify the true statement. Okay, I'm hoping that you have answered that. I'm going to move on to the answer. Okay, so the true statement here is that molecules in fats are packed more closely together than those in oils. I would forgive you, we didn't really talk a lot about the amount of energy stored in fats and oils. We did say that they are concentrated stores of energy, but I don't think we really compared them with carbohydrates. But this one is definitely correct. So in a multiple choice question, if you've got one that you think maybe, but you've got one that you know is definitely correct, then obviously go for the one that you're most confident on, because in chemistry there's only ever going to be one correct answer to a multiple choice question. So we're going to begin by looking at the soap making process, and that will lead us on to look at the structure of soaps. It would be helpful if you could turn to page 17 of your notes if you haven't done so already. So on this slide you can see a couple of images which illustrate the soap making process. Soap making is actually a remarkably simple process, and it's been done since ancient times. Soap's an ancient product. So what happens, the basics of soap making is that you take edible fat or oil. So soap can be made from plant oils like palm oil, coconut oil, olive oil, or it can be made from animal lard, although that isn't done so much nowadays. And you basically take your oil or fat and you boil it up with an alkali. So the starting reaction is done in a kind of liquidy state, and the soap can then be poured into a mould where it cools and solidifies and hardens. It can be dried out as well, and then it can just be sliced into the shapes that you want. So the process was given the name saponification, so you might see that name in the context of soap making, although you don't need to learn that name for the higher course. So what we now understand is that the chemical reaction involved, so we've got our fat or oil, and like I say, historically this was done with plant ashes, but it was known to be something alkaline that was needed. And what we now understand is that soaps are produced by the alkaline hydrolysis of edible fats and oils to give the sodium or potassium salts of fatty acids. So we're going to look at this process in more detail over the next couple of slides, and then we're going to look at a little animation on Scholar as well. So the key thing to take is that soaps, what they actually are the sodium or potassium salts of fatty acids. You might need to add in or potassium into your notes because I haven't put that in. And they're obtained by reacting fats or oils with an alkali. So how does this all work? So we can use these 2 alkalis here, sodium hydroxide or potassium hydroxide. So remember, fats and oils are esters of glycerol with fatty acids. We've discussed this already. We can have different fatty acids in each molecule of fat or oil. So the fatty acids might be all identical, might be different from each other, or they might be all different. So we can have saturated or unsaturated fats and oils. They can also be called glycerides because they're esters of glycerol, but you don't really need to remember that name. And so if you remember the basic structure, you've got your 3 atoms down the middle here. These are the carbons in the glycerol backbone. And then each fat or oil molecule has these 3 fatty acid chains coming off the glycerol backbone. So soaps are salts of these fatty acids, and in order to produce the salts of these fatty acids, the first thing that we've got to do is break down the fat molecule. So this is just a little recap again. Our saturated fats can pack closely together, leading to stronger intermolecular forces and higher melting points, and our unsaturated, more probably oils, if they're unsaturated, they pack more loosely together, leading to weaker van der Waals forces and lower melting points. Anyway, let's get back to talking about alkaline hydrolysis to produce the salts of fatty acids. Okay, so fats and oils are converted directly to soaps by alkaline hydrolysis, and there are 2 stages to this. So the first stage is the hydrolysis stage. So this is something that we've looked at before in the context of fats and oils. We've looked at how the ester can be broken back down into glycerol and carboxylic acids. And then the second stage is that the soap is formed by the alkali, so the alkali part of this alkaline hydrolysis neutralizing the carboxylic acids that were formed in the first stage. So again, we have looked at the neutralization reactions of carboxylic acids, so hopefully this will be reasonably familiar. This equation here gives an overview of the process. So we've got our ester here, our fat molecule, and we're reacting that with an alkali. We are then splitting that into the 2 components, the glycerol and the fatty acids. So we get glycerol produced. So glycerol is actually also a component of soap. And then we get our soaps, which are our salts of the fatty acids. So if it wasn't a salt, if there wasn't any alkali here, this would be the carboxyl group, carbon double bond oxygen with an OH. But because that's been neutralized, the alkali has taken that hydrogen atom away from the carboxyl group to produce an ion, which is then attracted to the sodium ion from the alkali, and water would also be produced. So that hasn't been shown in this equation. So we're just going to look at this process in a little bit more detail using the Scholar animation. Okay, so this animation is titled Saponification for soap making. So again, you can see our fat or oil molecule here, and we're going to look at the alkaline hydrolysis process. So it's called alkaline hydrolysis, but technically it probably happens in the reverse order, hydrolysis and then reaction with the alkali. But to be honest, during the soap making process, all of this is kind of happening at once, so don't worry too much about the order of things. So most of the time in these equations, in the equation in your notes on page 17, all we're showing is the fat or oil and the sodium hydroxide, but it is hydrolysis, water is involved as well. So the water is shown in this animation here. So our water molecule is splitting that ester link to create the hydroxyl group and carboxyl group. The carboxyl group then reacts with the alkali to give water and the salt of that carboxylic acid. So when we look at this again, I'll just talk a little bit about how that salt's formed. So again, we've got our water splitting the ester link, regenerating the carboxyl group and the hydroxyl group. When our carboxyl group reacts with the alkali, you can see that a bond is formed between the oxygen of the hydroxide ion and the hydrogen of the carboxyl group. Both electrons that were in the bond between the hydrogen and the oxygen of the carboxyl group get transferred to this oxygen atom, which is what leaves this as then an ion with a negative charge here. So one last time, we'll just look at this again. So we've got hydrolysis, splitting of the ester link, and then we have neutralization. So the electrons in this bond are being transferred to this oxygen atom to leave it with a negative charge. And that neutralization reaction, remember, all neutralization reactions produce a salt and water. But like I say in your notes, you don't have the waters shown in that equation, and we tend not to show the waters, but they are involved, so that's important to remember that water is necessary for this process. Okay, so we've looked at how soaps are produced by the alkaline hydrolysis of fats and oils. You should be able to answer question 1 on page 17 of your notes just by a careful look at this equation here. So you're just asked about the mole ratio for glycerol to soap produced in that reaction. We're now going to have a little look at the structure of these soap molecules in more detail, and that's going to help us to understand the cleansing action of soaps, so how soaps actually work. So, there's a clue already on this slide. Soaps are very similar to something that we've looked at already. And so they're the salts of fatty acids, and they're produced by alkaline hydrolysis. And when we look at the structure of soaps, we see something familiar. So soaps have this structure that's very similar to a fatty acid, except we've got an ionic head, if you like, to the molecule here. So we've got this long hydrocarbon tail, which is hydrophobic, and then we have an ion at one end of the molecule, and ionic compounds tend to dissolve well in water because the highly charged ions can interact quite strongly with the water molecules. And so the ionic head of the soap molecule is hydrophilic, meaning it's water loving, it dissolves well in water. So we're now going to look at how that allows soap to have the effect that it does. Okay, so if you turn to page 18 of your notes, you've got something very similar to what's on these slides. We're going to look at sort of 4 stages of how soap works. What I've done on page 18 is I filled in the kind of text, the writing part, and what I'd like you to do is to add in the diagrams that are needed for explaining each step. So we've kind of been through this already, so the special properties of soap are due to the structure of its molecules. We've got this long hydrocarbon tail, which behaves like a hydrocarbon molecule and dissolves well in other liquids with hydrocarbon chains such as oils, so this hydrophobic end. And then we've got this head end, which is like a sodium salt, so salts like sodium chloride are able to dissolve well in water. Now, I wouldn't bother drawing this top structure out, but what I'd like you to do in section 1 of your diagram on page 18, I'd like you to copy out this simplified model of a soap molecule. So we just represent it similarly to the way we did emulsifiers. We're just going to draw a line for the hydrocarbon tail. If you want to draw a zigzag line, you can, but it's not necessarily. We're just going to draw a line for the hydrocarbon tail and a circle for the ionic head. And make sure you label those in your diagram. And using this simplified picture makes it easier to explain the cleansing action of soap molecules. Okay, so once you've drawn this, we're going to take a look at section 2. And in section 2, you're going to draw yourself a nice blob of grease. So imagine that you're doing the washing up and you've had something delicious, like maybe like fried eggs for breakfast or something like that, but the plate's got really greasy and the frying pan is even more greasy. Disaster. But it's okay because you have soap. So you're going to draw yourself a nice blob of grease on your diagram, and what happens is in our soap, with our soap molecules, we've got the hydrocarbon tails, they are going to dissolve in the grease, but the ionic heads remain in the water, and the sodium ions also become free to move around in the water as well. So we get this this kind of picture here where we've got our tails of our soap molecules in the grease and the heads dissolving well in the water. So if you need to pause the video now while you draw that. Okay, so we're now going to look at step 3 and 4. So we've got our hydrophobic. In step 2 we had our hydrophobic tails dissolving in the grease and the ionic heads dissolving in the water. When we shake or agitate the water, that helps to break the grease loose. So you might realise that if you just pour some washing up liquids onto your frying pan and then try and rinse it, it's not really going to help to get the grease loose. You have to agitate it, and so using a sponge scrubbing helps this process, and heat also helps this process. So that's why we tend to use hot water when we're doing the washing up. So heat and agitation allow us to break the grease into lots of very tiny globules coated in soap molecules. And these little globules are so tiny that they float suspended in the water. So this is very similar to the way emulsifiers work. These soap molecules effectively stabilise the droplets of oil because each droplet of oil or grease is surrounded by these hydrophilic heads of the soap molecules. Then they can interact well with the water. They can become stabilised and float around in the water without coalescing, which means kind of clumping back together. Something about the soap molecules which helps to stop these globs clumping back together is the charges of the soap molecules. So our negatively charged hydrophilic ionic heads of the soap molecules repel each other, and that prevents these globules of grease joining up again to form a greasy blob. So structures like this with this shape, with all the hydrocarbon hydrophobic tails pointing in to the centre and the hydrophilic heads around the outside, these can be known as micelles. You may have heard of it, may have come across these before. Even if we didn't have any grease, you probably know that soap does appear to dissolve in water, and that's because even without any grease, the soap molecules can form these little micelles which can then be suspended in the water. So even without the blob of grease there, the hydrocarbon tails, the hydrophobic tails of the soap molecules would all end up pointing together, because the hydrophobic tails interact better with each other than with the water molecules, and they tend to stick together, and you'll get these hydrophilic heads all around the outside. And this forming these little structures, like I say, is how soaps can dissolve in water, and how soaps can help to dissolve fats or oils in water as well. So once you've got these micelles, once you've got these little suspended globules of grease that are floating well in the water, that then allows you to rinse both the soap and grease away from your dishes. So we've looked at the cleansing action of soaps, how they work. So just a little summary: they work by breaking oil and grease into tiny droplets which can mix with water. So I think that's quite a nice little summary. You might want to add that in somewhere on page 18, or probably maybe down the bottom if you've got some space, because I think that's quite a nice little summary. And again, this is just a recap, and that works. So they work by breaking oil and grease into tiny droplets which can mix with water, and that is possible because of the structure of their molecules, this hydrophobic tail and the hydrophilic head. So another little kind of point of interest, you don't need to know this at all, but biologists might have learned a little bit about the structure of the cell membrane. So the cell membrane of our cells in the body is composed of something called a phospholipid bilayer, and so the phospholipid molecules have a similar structure to soaps. They have this hydrophilic head and hydrophobic tail, and that allows the formation of this bilayer sheet, which is essential. This is how cell membranes are formed, and this allows the cell to keep certain things inside the cell and keep certain things out, and then you end up with different channels within the cell membrane to allow transport of essential things across the cell. So I find that quite interesting, how the structure of soaps is quite closely linked to the structure of these phospholipids which form cell membranes. So that's us covered the kind of essentials for soaps. So you should be able to explain how soaps are made, giving details of the reaction. So you should be able to name the reaction and see what the reactants and products are. And you should be able to describe the cleansing action of soaps based on the hydrophobic and hydrophilic nature of soap molecules using diagrams to help you. So this is quite a common explain question in higher papers, so it's good practice to make sure you can draw the diagrams and remember how to explain what's happening as well, and use these keywords here: hydrophobic and hydrophilic. So the last part of this little section is about detergents. Detergents are very similar to soaps, and rather than me talking about them, I've just taken a little article that I found online and copied it into your notes. So what I'd like you to do is read the information on page 19 and answer the questions. What you're wanting to focus on is being able to explain what is meant by hard water and describing its impacts on soap. And make sure you know some of the similarities and differences between soaps and detergents, especially in relation to hard water. Detergents, don't get too bogged down in the details of detergents. Just focus on answering the questions and making sure you know what's meant by hard water and the differences between soaps and detergents. You could look into this, you could spend ages researching detergents and their different structures and how they're made and things. But you don't need to know a lot of detail about detergents. So like I say, try not to get too bogged down in it. I hope you found this section interesting, and I look forward to seeing you back in class very soon.